Welcome to Lecture 6.3, Matrices and Systems of Equations. Today we're going to solve systems of equations using matrices, and we'll be using row operations or a calculator. So we've been looking at linear equations in 2 and 3 variables. And here we have a linear system, 4x plus 2y equals negative 3. And x plus 5y equals negative 4. We can express this system as an augmented matrix. And what you'll notice here is that what we've done is we've taken the coefficients from each equation and moved them into a row. So the first equation is 4x plus 2y equals negative 3. We just move the numbers or the coefficients, so we get 4, 2, negative 3. The second row is the second equation, so each row is an equation, and here we get 1, 5, negative 4. In front of the x is a 1, even though you can't see it, a 5 in front of y, and a negative 4. It's important if you're going to be building augmented matrices that you have these in standard form with the variables in alphabetical order and lined up. Okay. Here, an augmented matrix omits the variables and replaces the equal sign with the vertical line. A rectangular array of numbers such as 4, 2, negative 3, 1, 5, negative 4 is called a matrix. If you have more than one matrix, the plural of matrix is matrices. The matrix is an augmented matrix because it contains not only the coefficients, which you see on the left side of the line, the coefficients of the variables, the multipliers in front of the variables, but also the constant terms on the right side of the equation or the right side of the straight line. And you can think of this straight line in the augmented matrix as an equal sign. Another matrix, a subset of this matrix, 4, 2, 1, 5, is called the coefficient matrix because you can see that it is the coefficients on each of the variables in the equation. The rows of a matrix are horizontal, they go left to right. The columns of a matrix are vertical, they go up and down. The matrix shown has 2 rows, right? We go across, 1, 2, 2 rows, and 3 columns. Columns are up and down, 1, 2, 3, okay? A matrix with m rows and n columns is said to be of the order m by n. You can think of this as how we talk about the size of a room. It's 10 by 13. And so the order of a matrix is just kind of giving the dimensions of the matrix, specifically the number of rows, by the number of columns. So this matrix here is of order 2 by 3. 2 rows, 1, 2, and 3 columns, 1, 2, 3. So the order of a matrix is just giving its dimension, specifically in terms of rows by columns. When the rows and the columns are equal, that's what m equals n means, the matrix is said to be a square matrix, and that's pretty intuitive. So if we had 2 rows and 2 columns, you would notice you'd have a square matrix, the same height and width or same number of rows and columns. So we're going to do something first called Gaussian elimination with matrices, and this is when we use row equivalent operations. Basically what we're doing is we're manipulating each row of the matrix just like we do when we manipulate an equation. You know, we add something to both sides, multiply something to both sides, etc., so that we can solve it. And so we're going to do the same thing with matrices. It's a little bit complicated, and you need to know these 3 rules. You can swap any 2 rows. So you can turn row 1 into row 2 and vice versa, okay? You can multiply each entry in a row by the same constant, but the constant cannot be 0. You can add a non-zero multiple of one row to another row. And we use these operations above on an augmented matrix to solve the system. Okay. So I've put the rules up here in this box in the top right, so we remember them. And here we have a system of equations, 3 equations with 3 variables. Typically, you need the same number of equations as you have variables in order to solve. And so the first thing we want to do is to create an augmented matrix. Okay. Notice in the last row, we don't have a y term, so we're going to use 0 for that missing y term. We cannot leave blanks in a matrix. And so we get the matrix here. The first row of numbers should be 2, -1, 1, 8, and you can see that there. The second row would be 1, -3, -2, -1. And the third row should be 4, 0, 5, 23. Okay? And so that's the first thing we need to do when we have a system of equations. Make sure they're in standard form. That means each of the variables is kind of in a column form, and all the constants are on the right side of the equal sign. Now our goal is to find a row equivalent matrix of this form where there are ones on the downward diagonal on the coefficient side, and everything below the ones on that side is zeros. So ones on the downward diagonal and zeros below. Now why do we want that? Because notice what happens is the last equation we've already solved for one variable. We know that z equals f. Now each of these a, b, c, d, e, f are just representing numbers. Doesn't matter what these are, and that's why they're variables there. What we're trying to do is create a 1 on the downward diagonal and zeros below. All these other numbers, it doesn't matter. Because now we could solve this matrix, we could solve for each of the variables by working from the bottom up. If we convert the last row into an equation, we get z equals f. If we go one row up, we get 1y plus dz equals e. Well, if we know what z is, we can plug that in, and then we can solve for y. And if we go up to the top row, we get 1x plus ay plus bz equals c. Since by this time we know what y equals by solving this equation and z equals, we can now solve for x. Okay. So the first thing we need to do is we're going to start in the upper right corner. We're going to work a column at a time. And the first thing we need to do is to change the 2 in our original matrix. We need this to be a 1. Remember, we're trying to transform this matrix to look like this, that there will be 1s in the downward diagonal and zeros beneath those 1s. Okay? So how can we do that? Let's change row 1, first element to a 1, simply by swapping rows 1 and 2. Remember, the first rule says we can interchange any 2 rows. And notice in row 2, we already have a 1 in that first column position. So if we just swap row 1 and row 2, we've handled that first bit. Okay? Our new row 1 is simply row 2, and our new row 2 is simply row 1. So all we did was swap row 1 and row 2. All right, and that's one of the things that we can do, is to interchange any rows. All right, so this is our new matrix that we're going to solve. Now when we're doing these, we need to again work column by column. So we got the 1, and now we're going to go down and we're going to create zeros. All right, there's our matrix where we left it off. Our next step is to change the first element in rows 2 and 3 to a 0. Okay, we need both of those numbers there in that first column to be zeros because we're trying to build that reduced row epsilon form. I'm sorry, the row epsilon form. All right, what we're going to do here is we're going to multiply row 1 by the opposite of the number that we want to be a 0 and then add it to that row. Okay, so for example, we're going to multiply to get a 0 in this place in row 2. We're going to multiply row 1 by -2. We're going to take that number and its opposite. We're going to multiply row 1 by -2 and then add it to row 2. Now let's see what that looks like. So notice if we multiply, the opposite of 2 is -2. We're going to multiply the row with the 1 in that same column position. So -2 times 1 is -2. -2 times -3 is 6. -2 times -2 is +4, and -2 times -1 is +2. So this is -2 times row 1, and then we're going to add it to the row 2. Our row 2 is 2, negative 1, 1, 8, 2, negative 1, 1, 8. When we add these members down, we get 0, 5, 5, and 10. And this gives us our new row 2. We're going to do the same thing with row 3. We're going to take the opposite of this number 4 and multiply it times row 1. So we get negative 4 times row 1. And then we add it to row 3. And when we do that, we get this new bottom row here. Okay? So again, when we're trying to change these all into ones on the downward diagonal, we work a column at a time and from top to bottom. So our next move is to try to convert this second element in row 2 into a 1. Now, ones are easy to create because all we have to do is multiply. Remember, we can multiply each entry in a row by a non-zero constant. And when you multiply a number by its reciprocal, you get 1. The reciprocal of 5 is 1/5, and 1/5 times 5 is 1. So we're just going to multiply this entire row by the reciprocal of the number in the position where we want a 1. We will do this every time we want a 1. Ones are the easiest thing to create because we only need to do multiplication of a row. Okay, so here we just have new row 2 is 1/5 times the old row 2. So 0 times 1/5 is 0. 5 times 1/5 is 1. 5 times 1/5 is 1, and 10 times 1/5 is 2. All right, so notice now we have that 1 in the position that we wanted it. Here's where we left off. Sorry we have to go over slides here, but here's where we left it off. And now we need to create another 0. We need a 0 beneath the 1. Remember, we're working the second column now. But we're going to do these zeros the same way. Do you remember how we did it the last time to create these two zeros? We take the opposite of the number in the position we want a 0, multiply it times the row with the 1 in that same column that we're going to use, and then add them together. Okay, we need to change the second element in row 3 to a 0 by multiplying row 2 by the opposite of the coefficient. The opposite of this coefficient is negative 12, and adding to row. So here I did it again. So if we take negative 12, the opposite of this number we want to be a 0, times row 2, we get negative 12 times 0, 0. Negative 12 times 1, negative 12. Negative 12 times 1, negative 12. Negative 12 times 2, negative 24. We then add it to the row where we want the 0. 0, 12, 13, 27. This is row 3. And the bottom is our new row 3. 0 plus 0 is 0. Negative 12 and 12 is 0. Negative 12 and 13 is 1. And negative 24 and 27 is 3. And so this is what our matrix looks like now. And conveniently, when we fixed that 0, we also got a 1 in our final spot. So that's awesome. So we're actually done. We've created the reduced epsilon, the reduced row form. We've got ones on the downward diagonal, zeros down below, and so now we're ready to solve the problem. And we do that by converting back to equations and solving by working from the bottom up. So notice the first equation would be 1x minus 3y minus 2z equals negative 1. X minus 3y minus 2z equals negative 1. The second equation has 0x, so we're going to skip that. 1y plus 1z equals 2, or y plus z equals 2. And then the last row is our final equation, and that just says there's a 0x and a 0y, so those don't matter. And we get z, 1z equals 3, or z equals 3. And so now we just plug in 3 to the equation above it. Y plus 3 equals 2. So we get y equals negative 1. Then we plug in 3 for z, negative 1 for y, and solve for x, and we get x equals 2. So again, we work backwards from the bottom up, and we get a triple, 2, negative 1, 3. And this checks is if you plug it into each of those original equations, you will see that it does indeed make each statement true. All right. We're going to look at a different way to do this exact same problem. And it's called reduced row echelon form. Okay. And each column that contains a leading one has zeros everywhere else. Okay. So this is what a reduced row epsilon form of a matrix looks like. In the last problem, we created ones on the downward diagonal and zeros below. Here, we are also going to create zeros above this downward diagonal of ones. Now, why do we do that? Because now, notice our answers are already done. X equals 2, y equals -1, and z equals 3, right? Because we have 0x plus 0y plus z equals 3, which just simplifies into 0 equals 3. Okay, so this was the original augmented matrix from the original equations way back that we've been looking at throughout this lecture. And so the first thing we need to do is to use our calculator to build a matrix. Okay, the matrix function is on the left column about 3 or 4 buttons down. You'll see a button that says x raised to the power of -1. Above that, you'll see in blue the word matrix, and the way you accent those functions, those are the second functions, so you're going to use the second button. So the first thing we need to do is to build this matrix. If you hit the second button and then hit the matrix button, which is that x -1 button, you'll see across the menu of your calculator 3 menus across the top. So tab over to where it says edit and then hit enter. Here you will then enter the size of the matrix you want to enter. In this case, we have 3 rows and 4 columns, so enter 3 by 4, and then hit enter. Now it's going to ask you to enter each of the elements, and it'll start at the upper left and go across. So you're going to hit 2, enter, -1, enter, 1, enter, 8, enter, 1, enter, -3, enter, -2, enter, -1, enter, 4, enter, 0, enter, 5, enter, 23, enter. You have now built your matrix, and so we need to get out of there. So hit the second button and then hit the quit button. Okay, so you built the matrix, we go back out and we start all over again. So now we need to solve the matrix. You've got this built in. So what we're going to do is you're going to hit the second button and the matrix button again, the x to the -1, but instead of going over to edit is where you build matrices, we're going to start doing some math with the matrices. So this is the middle menu. So tab over to math and hit enter. Now this will give you a menu with a bunch of different functions. So page down until you hit item B, which is RREF, which stands for reduced row epsilon form. Once you hit to B, hit enter. Now you've got this RREF on your menus on your screen of your calculator, and you have to tell it which matrix you want to reduce to row echelon form. So hit second button, hit the matrix button, and now you should just be able to select matrix A or wherever you entered that matrix and hit enter again. And then you will see this in your window of your calculator, this reduced row epsilon form matrix, and then you simply interpret the answer, x, y, z, or as a tripled pair. I don't know, these values are not right. -14, this should be 2, -1, and 3. That's just there to make sure that you stay awake. All right, so your calculator can do a lot of this work. It can really help you out. No one does matrices by hand anymore with this reduced row operations. Everyone uses tools like Excel or a calculator. So just a couple last things to be mindful of. When a row consists entirely of zeros, the equations are dependent. So here you can see the bottom row is all zeros. Okay. Now remember, when all the variables disappear and you get a true statement, that means that they're really the same thing, or there's an infinite number of solutions. But notice we can rewrite the first row as x plus 4z equals -6 and y plus 4z equals 8. Okay. When we have a dependent system like this, the way that we write the pairs is we solve for x in the first equation. we solve for y in the second equation, and then we just leave z as that variable that can change every time. Finally, the last thing we have is another special system. When we obtain a row whose only non-zero entry occurs in the last column, and you can see that here in row 3, we have an inconsistent system of equations. For example, in the bottom matrix, notice that last row corresponds to a false equation of 0 equals 9. So we know the original system has no solution. So again, if you have zeros in the coefficients and a constant that's not 0 in the last position, you know that there is no solution to this system. Okay? All right. Hopefully this helps you, and have a great day.